All right, so we're going to move on with notes from packet unit 2.1 to 2.3, specifically pages G. Some of the stuff I already have filled in. It's just going to be a summary of the 2.2 notes and then an application of it. So in 2.2, we talked about some basic differentiation rules. And so if we consider this constant function, and if we graph it, f of x equals 4 is the same thing as y equals 4. So if I graph that function, I am going to have just a horizontal line through the number 4, and the slope or derivative of any constant function, the slope, is always equal to 0. But now what I want you to understand is the connection to the idea of derivative. That's just me drawing an arrow. F prime of x is equal to d dx, another way you can denote it, of 4, which is equal to 0. So the slope is 0, the derivative is 0 for this function. That is the constant rule. The derivative of any constant is 0. Then we also had the power rule, which was where you have a polynomial function or you have a function that's got a power, and you would bring down the n as a coefficient, then subtract by 1. Okay? So keep in mind that that rule is, when we do the derivative, it would be n times x, n minus 1. So there is your derivative answer for the power rule. Now the corollary to that is if we just have x, the derivative of x is just 1. If you think about what that looks like in terms of a graph, that is the parent linear function, and no matter what, the slope of this parent linear function is always 1. Keep in mind too, there is a constant, sometime there's going to be another rule later that I'm going to talk about or bring back up if there is an existing coefficient in front of the original term. All right, so examples of power rules. I'm just going to go through this quickly, see if you can follow. We are doing derivative using the power rule. Rewrite before you do the calculus. Keep in mind we have to subtract 1 from 1/3, which really means 1/3 minus 3 over 3. So in these beginning set of notes, I'm going to write that out so you can see it, but eventually I'm not going to write this step. You will just have to know you're subtracting 1. Still rewriting. Now I'll do the calculus. Little note down here, to use power rule, you want each term to have exponents in the numerator, whether they are positive or negative or could be a fraction exponent as well. Flipping over to the next page, G, I've already written on the top, f of x equals x to the 4th. So we have a quartic function here. And let's say we want to find the slope of the graph at these specific points. Keep in mind slope now is derivative. And then we're going to evaluate. So instantaneous rate of change. So here's my function. I'm going to write f prime of x using our power rule. Then I'm going to apply it. All right, so in summary of this problem, if I were to draw a tangent line at these points, if we draw a tangent line at x equals 0, the slope of the curve at that point is 0, and so is the slope of the tangent line. If I draw a tangent line to the graph at x equals -1, I'm going to dash this one. Notice how my tangent line decreases. So therefore, it makes sense to have a slope of -4. And then if I go in the other direction, if I sketch a tangent line to the graph of the function, both the graph and the tangent line have a slope of 4 at x equals 1. All right, so next example, find slope of the tangent line. So thinking about that last problem there. So I have the parent quadratic. Question could be, what is the derivative, or what is the slope of the tangent line at a specific point? So the slope of the tangent line at x equals -2 is -4. All right, so the third differentiation rule that we talked about was the constant multiple rule. And this is, to me, a variation of the power rule, where you are bringing down, if you have a constant that's already in front, you just multiply it using the power rule. We already did these in the notes from 2.2, so I'm going to put 2.2 notes. We did maybe not all of them, but a variation of them. All right, then we did the sum and difference rules. So really you can just break these apart. It's almost like a variation of distributive property. So you're going to do the derivative of each term separately. Likewise, you would do the derivative of each term, and then you would subtract the two derivatives. So some quick examples. Find the derivative. 3 separate terms. So first derivative, f of x's derivative, or I should say the derivative of the first term. This is just a linear piece, quote unquote. So remember, that's a power of 1. So just the derivative there. And then the derivative of a constant, like when I started these notes, is 0. Sine and cosine. I had given you these the other day. I'm going to rewrite them again. Derivative of sine is cosine. The derivative of cosine is negative sine. Again, these were in the 2.2 notes that you can reference. Finding the derivatives. Let me just do that one really quick. This one is dy dx is equal to, because there's a 1 here, 1 plus cosine x. Okay. What did I wanted to get to in this section was the introduction to particle motion. So on this next page, I'm going to kind of show the notes and then talk about them. And some of the stuff I already have pre-written in. I don't want to go word for word. I'm going to try to summarize as best as I can, but you can read the word for word. So here's this idea of derivative. Derivative gives slope at any point on a graph. So now we're going to say that derivative is also synonymous with this idea of instantaneous rate of change. Applications include derivative in science and economics. So some examples of changing concepts: population growth rates, water flow rates. A huge one that's in the news right now is the spread of the coronavirus, the rate at which it's spreading or slowing down, the models that are being used to help open up the country again is completely based on mathematics and most likely calculus. If we have a high rate of change, that means that people are being infected more quickly or at a more rapid rate. So what we're going to do now is going down here. When we start talking about physics, some of you have already had physics, AP Physics. One of the most common uses is to describe particle motion, whether a particle is moving along a horizontal or vertical line, but also motion of vehicles as well. So in order to start with any type of particle motion or object motion, we would have to have a position function. And the position of the object or particle is always based off of its distance from the origin. So if a function gives us the position relative to the origin of an object as a function of time, we call it a position function. So I am going to write that in purple up here. A lot of times a position function in calculus will be listed as either h of t, physics or calculus, or now you might see s of t, or even though it's a little bit confusing, you might see x of t. Typically, the x of t is particle motion along the x-axis. So even though we think of x as an input, in this case, this would be an output because the input would be the t variable. So I'll address that as we are exposed to those types of problems. Okay? So a position function is always with some type of relationship with respect to the origin. So in algebra, if we have this formula, distance equals rate times time, and we needed to find the rate, we simply did algebra and properties of equality. We divided both sides by t, or the time. In physics, you may have seen a position function also written as x of t or s of t. And I'm going to hide this again over here, trying to be crafty with this. Okay, then here comes this new introduction. We go from position function, and then we've been talking about average rate of change. So let's, instead of saying the word rate of change, let's say velocity. So average velocity. Average velocity is a slope. So if we talked about our position being s of t, if we want to talk about the average velocity, it means how is the position changing over time? How is the position changing over time? But we're going to use variables of a and b because now we're going to mark some intervals on a graph. So average velocity, I'm going to keep this here. Think about average rate of change that we did. I don't know if it was notes E or F, but let's say that we have, and I'm going to cover this guy up. Let's say that we have a billiard ball, like when you play pool, is dropped from a height of 100 feet and is given by this position function here. So back in algebra, or algebra 2, this 100, the constant, is the original position or original height of the object that's being dropped. So notice it is being dropped, it is not being launched. So that is the original height. And then the negative 16 has to do with the gravitational pull and acceleration. Once I reveal this over here, you'll see some familiar formulas. So here is our position function. Okay, so basically this ball is being dropped from 100 feet. Like if there's a building, it's just going down and being dropped. Okay. What we need to do is find the average velocity. So keep in mind that that means average rate of change, like we did in some previous notes. So the way that I did it, so if we're looking at average velocity over each of the time intervals, so now these intervals are going to be given as interval notation, so from 1 second to 1.5 seconds. So that would mean that we are talking about like from here to here. So average rate of change, I had you put your inputs here, and then I had you evaluate. So you took the 1, you put it in here, got 84, put 1.5, evaluated with for t squared, and got 64. So here is your change in position over your change in time. Just like I had up here, change in position over change in time. So between 1 and 1.5, so this little piece right here, let's say, that little piece, the average velocity, because it's changing, but the average velocity is negative 40 feet per second. Now the reason it's negative is because velocity denotes a direction as well. So because it's going down, it is a negative. You could figure out that for these other two time intervals too and see by changing the time intervals. Like this is a more condensed time interval, so you're going to get a different number. You can check your notes with what I have updated in Schoology. So now what we did was we just did average velocity. what if we wanted to find what the velocity is at an instant? So let's say I want to specifically find what is the velocity of the object, like right here at, let's say, 1.35, exactly at 1.35. So introducing this idea of derivative, okay? Over here, what I'd like you to do is this idea of physics derivative, or now we can even say calculus. When we talk about, if we're given a position function here, if we find the first derivative of the position function, it is going to be the velocity function. So this is velocity. The first derivative of a position function is a velocity function. And this is instantaneous, or as best as we can get to instantaneous, versus average velocity. The second derivative, so velocity is the rate of change of position over time. Then the second derivative is the rate of change of velocity over time. And that, the second derivative of position, which is the first derivative of velocity, is acceleration, which hopefully makes sense to you as well. So the rate at which velocity changes over time is acceleration. Okay, so we go from position to velocity to acceleration. Moving on to the next page. Again, I have pre-filled in some information. And so as I look at this page here, so we were finding average velocity using this formula. So that's over a certain time span. But now if we want to find instantaneous velocity, we're going to talk about derivative at a specific moment. So the derivative of position is velocity, and that's what I gave on the last sheet. Okay. So this idea of free fall, oops, I don't even know if you saw any of that. So fill in the rest of this. I think it was off the screen, my bad. Average velocity over time, over a time span, your change in your position over change in time. So average velocity is a quotient, meaning a division problem. Then if we want to find instantaneous velocity, it's derivative. And that's when we would use the new notation and our shortcuts and all of our new rules. So back in algebra, when we talked about a free-falling object under gravity, in algebra, these were the familiar formulas that we saw. So they were quadratic. So an object can be dropped, or an object can be launched or thrown up in the air and then come back down. So in this case here, there might be an initial velocity, like if an object is being launched up in the air and then comes back down, or somebody's on a diving board, goes up and comes back down, or if a ball is being hit, goes up and comes back down. So in that case, we have an initial velocity. Typically, when you see the negative 4.9 as the lead coefficient, those units are in meters for the unit of length. And if you see a negative 16, those units are in feet, our customary system. In physics, there was a formula that is that you will see as well. It has I think a 1/2 in front of it. Oh, here it is, right here. So in physics, this was the formula that you were presented with for free-falling objects, because there's that extra value for gravity. And in calculus, we only talk about stuff pretty much on the surface of the Earth. And this G and this 1/2, they will become a product, and that's how you get the negative 4.9 and the negative 16, depending on the gravity. Okay, so filling out the middle here. Velocity includes direction. So that's what we saw in the last example when we had a negative answer, which means it can be negative. Now, this is not crossing a line off. The difference between velocity and speed is the absolute value of velocity because it does not tell direction. Thus, it's always positive. So what I'm going to do is I'm going to write speed is equal to the absolute value of velocity. Super big popular question on the AP exam. If you're asked to find the speed of an object, once you get this answer, like we had on the last problem over here, if it said the word speed, you just do the absolute value of that, which would be 40 feet per second. Okay, so let's again address some algebra. So if we have a diver jumping from a platform that's 32 feet above the water, they gave you the formula already. Here's your original height. And it also gives you that the original or initial velocity is 16, which is indicating he's jumping up and then coming back down. That's not mentioned in the wording, but is given to you because of the word feet. The lead coefficient is negative 16. So you shouldn't have to create these equations. You might in the homework a couple of times, so if you need extra help, please let me know. And then what I would like you to do is answer these other two questions. So this is an algebra question. When does the diver hit the water? Which means that you're taking this position function and you're setting it equal to 0 to find the time. So when you set it equal to 0, here we have this. I'm going to factor out a negative 16, still keeping it equal to 0. Solving a quadratic, you could do quadratic formula if you want, or factor. So t will either be 2 seconds or negative 1. Now, in terms of the context of the problem, we would throw that answer out. So after 2 seconds, that's when the diver hits the water. Then, in part B, it says, what is the diver's velocity at impact? So that's asking for an instantaneous idea. Specifically, what is the velocity at a specific time? That specific time is at 2. So now we're going to do calculus. We're going to take the derivative of this position function to get the velocity. So the derivative of the position function to get the velocity. That means I'm going to do negative 16 times 2 and get 32t and then plus 16. So here's your velocity function based off of the derivative of the position function. Then specifically at 2, you take the number 2, you plug it in here, evaluate, and you will get your velocity. And again, I've got the negative 48. I guess I should have chose maybe some other numbers to deal with. So my velocity at the moment of impact is negative 48 feet per second. When you were in algebra, probably what you did was if you needed to find the velocity at impact, I'm trying to think what you probably did. I don't even know if you were looking for velocity. You probably in algebra just figured out the maximum height and things like that. You probably did not talk about the idea of velocity. Okay, so that is it for Notes G. Now you should be able to do the corresponding homework that is in your calendar.